now, while you sit here, a signal is traveling toward Earth. 23 watts. The power of a refrigerator.
Liftoff. We have a liftoff.
Moving at the speed
Come on,
of
you
light
can do
through
it.
absolute darkness.
We
It has
have
been
stage
traveling for
separation.
17 hours, crossing a
Interstellar
distance
space.
so vast that
After
if you
all
could
these
somehow
years.
walk it, you would die of old age 1,000
Incredible.
times
So,
before
if
reaching
we look
the
at this
source.
integral here,
The
we
signal
can see it
carries
simplifies
numbers,
using this
magnetic
identity,
field readings,
which then gives us the
particle
final solution.
counts, temperature data from an environment no human being will ever visit. It arrives at 3 massive radio dishes, 70 meters across, scattered across 3 continents, positioned so that at least one is always listening, always reaching out into the black, always waiting for those 23 watts to whisper home. The signal comes from a machine 15 billion miles away, farther than anything human-made has ever traveled, farther than the mind can properly hold. And the message it carries, translated from binary into meaning, says this: we are outside. Outside the heliosphere. Outside the bubble of our sun's influence. Outside the boundary where everything we have ever known ends and something else, something truly alien, begins. The machine sending this signal was built in 1977, before personal computers, before the internet, before most of the technology you use every day was even imagined. It has 69 kilobytes of memory, less than a single emoji on your phone, less than 1 second of the music you might be streaming right now. And yet it is out there, still functioning, still measuring, still transmitting, every single day, without fail, for 48 years. This is the story of that machine, and the story of the people who built it, guided it, and taught it against every law of entropy and cosmic indifference how to speak with eternity. If you were 17 years old in the summer of 1977, you might remember watching television on August 20th. The networks interrupted regular programming. Walter Cronkite's voice measured and authoritative filled living rooms across America. Today, a journey begins, a journey to Jupiter, and perhaps beyond. The camera showed Cape Canaveral. A Titan Centaur rocket gleaming white against the Florida humidity stood ready on the launch pad. Vapor vented from its liquid fuel tanks. The countdown progressed with mechanical precision. Engineers in short-sleeved shirts and thin ties monitored banks of switches and dials in mission control. Most viewers understood this as another space mission. America had been to the moon. We had sent probes to Mars. This was one more step in the progression of exploration. But what the broadcast did not say, what could not be said, because it would sound too much like science fiction, was this: the trajectory being executed was not designed to visit planets and return. It was designed to visit planets and then keep going. Out past the orbit of Neptune, out past the scattered rocks of the Kuiper Belt, out into a region of space so empty, so cold, so profoundly far from the sun that no human mind had ever seriously contemplated sending anything there. The rocket was not coming back. Neither was the machine it carried. Inside the nose cone, wrapped in gold thermal blankets that glinted like foil, sat an object roughly the size of a compact car. 1,800 pounds of aluminum, titanium, and copper. A 10-sided frame holding cameras, spectrometers, magnetometers, plasma detectors. Instruments designed to see things human eyes could never perceive, to measure forces invisible and deadly. At the heart of this machine, 3 radioisotope thermoelectric generators. Plutonium-238, glowing orange hot, decaying in a slow controlled burn, converting the heat of atomic decay into electricity, a nuclear heartbeat that would pulse for decades. The plutonium did not care about hope or dreams or human ambition. It simply decayed, one atom at a time, predictable, unstoppable. A countdown measured not in seconds but in half-lives, stretching across nearly 90 years. The machine had a name: Voyager 2, 10987. The engines ignited, a controlled explosion, millions of pounds of thrust. The rocket lifted slowly at first, then faster, climbing on a pillar of fire and smoke, arcing east over the Atlantic, accelerating to speeds where the air itself became a weapon. In a control room at the Jet Propulsion Laboratory in Pasadena, California, 2,600 miles away, men and women watched telemetry screens, confirming staging sequences, tracking trajectory, watching numbers scroll past that represented the difference between success and catastrophic failure. One of those people was Marcus Aldridge, 40 years old, graying at the temples, reading glasses perched on his nose. He had not slept properly in 3 days. His hands trembled slightly, not from fear, but from exhaustion and caffeine, and the weight of 12 years of calculation finally impossibly becoming real. Marcus had joined the Jet Propulsion Laboratory in 1965 as a young aerospace engineer, 28 years old. Fresh out of MIT with a head full of orbital mechanics and a conviction that humanity's future lay beyond Earth. They had given him a routine assignment: calculate possible trajectories for missions to the outer planets. He had been sketching orbital paths on a chalkboard at 2 in the morning, his wife 8 months pregnant at home sleeping, when he noticed something. An alignment. Jupiter, Saturn, Uranus, Neptune. The four giant planets would be arranged in a loose arc on the same side of the Sun in the late 1970s. Not a perfect line, not close together, but positioned in such a way that a spacecraft could use the gravity of each planet to fling itself toward the next. Gravity assist, planetary billiards. A spacecraft arriving at Jupiter with the right trajectory could steal a tiny fraction of the planet's orbital momentum, utterly negligible to Jupiter, but enough to accelerate the spacecraft to speeds no rocket could achieve alone. Then Saturn, then Uranus, then Neptune. One mission, 4 planets, 12 years instead of 40. Marcus had done the math 3 times to be certain, then a 4th time. Then he had walked to the office of his supervisor at 6 in the morning and shown him the numbers. This alignment, he had said, it happens once every 176 years. His supervisor had stared at the calculations, then looked up at Marcus. How long until the launch window closes? 12 years. The last time the planets had been aligned this way, Thomas Jefferson was president. The United States had 17 states. No one on Earth knew what a spacecraft was. No one had imagined internal combustion engines, electric light, radio flight, or atomic energy. The next time the alignment would occur, everyone alive in 1965 would be dead. Marcus called it the Grand Tour. The name stuck. NASA heard the proposal and did what large organizations do: they formed committees, commissioned studies, calculated budgets, designed increasingly elaborate mission architectures. By the early 1970s, the Grand Tour had grown into a 4-spacecraft program with cutting-edge technology and a price tag that made Congress physically uncomfortable. And then in 1973, it died. Budget cuts. The Apollo program was winding down. The shuttle was the priority, now reusable, economical, practical. Deep space exploration of empty planets seemed extravagant, unnecessary. The Grand Tour was canceled. Marcus had stood in his office, holding the memo, feeling 12 years of work dissolve into bureaucratic language and fiscal constraints. He had gone home that night and told his wife he was thinking about leaving JPL, finding something else. Something where the work mattered. She had listened, then said, "You calculated something no one else saw." They canceled one version. Calculate another. So he did. He and a small team, stubborn, sleep-deprived, refusing to let the dream die, came back with a stripped-down proposal. Not 4 spacecraft. 2. Not cutting-edge technology. Modified versions of the existing Mariner platform. Not an explicit promise to visit Uranus and Neptune. Just Jupiter and Saturn, officially. The budget roughly 1/3 of the original estimate. They called it Mariner Jupiter Saturn, a name designed to sound modest, bureaucratic, unlikely to attract attention or opposition. Congress somewhat grudgingly said yes. Marcus had learned something in that moment, something about compromise, about the difference between perfect dreams and achievable reality, about how sometimes you have to hide your ambitions inside language that sounds small, even when you are planning something immense. Because here is what the proposal did not say out loud. The trajectories for both spacecraft were designed with enough flexibility that if everything worked perfectly, if the instruments survived, if the plutonium lasted, if the spacecraft could be reprogrammed in flight, they could continue past Saturn, to Uranus, to Neptune. The Grand Tour was not dead, it was just disguised as something smaller. And on August 20th, 1977, the first piece of that disguised dream roared into the sky. 16 days later, on September 5th, Voyager 1 followed. Same rocket, same design, same plutonium heartbeat, but a different trajectory, faster, more direct, designed to reach Jupiter first despite launching second. The naming convention confused people then, and still does now. Voyager 2 launched first. Voyager 1 launched second. But the names were based on arrival order, not launch order, a piece of bureaucratic logic that makes perfect sense on paper and no sense at all in conversation. Both spacecraft were identical, twins, but they would have very different lives. Within the first year, Voyager 2's primary radio receiver failed, a catastrophic malfunction. The spacecraft could no longer hear commands from Earth using its main communication system. It switched automatically to its backup receiver. The backup worked, but it had a flaw: frequency drift, like a radio that slowly, imperceptibly changes station. The frequency it listened on shifted over time with temperature changes in the electronics. From that moment forward, every single command sent to Voyager 2 had to account for the drift. Engineers had to predict across hundreds of millions of miles, across hours of light-speed delay, exactly where the receiver's frequency would be when the signal arrived. One miscalculation meant the spacecraft would not hear the command. No hearing meant no response. No response meant losing control. Losing control meant losing the mission. A young flight controller named Daniel Brennan took responsibility for the frequency calculations. 27 years old, thin and tense with the kind of focus that made him forget to eat during critical operations. He built spreadsheets, actual paper spreadsheets in those early years, tracking the temperature cycles of the spacecraft, the drift rate of the backup receiver, the Doppler shift from the spacecraft's velocity. It's like, he explained once to a reporter, trying to throw a dart at a target. But the target is moving, and you are moving, and the dart takes 4 hours to arrive. And if you miss by 1 inch, you lose everything. The reporter had asked how many times they had missed. Daniel had smiled, exhausted. 0. We have missed 0 times. That answer would remain true for the next 48 years, but before the spacecraft launched, before the rockets ignited, before Marcus's calculations became metal and fire, there was a decision that had nothing to do with science or trajectories or planetary alignments, a decision about what these machines should carry beyond their instruments, beyond their cameras and sensors, a message. Frank Drake and Carl Sagan had convinced NASA to include a message on earlier Pioneer spacecraft, a simple plaque showing a man and a woman, a diagram of the solar system, and a map using pulsars to pinpoint Earth's location in the galaxy. The plaque had generated both excitement and controversy. Some loved it, some thought it was naive, some worried about broadcasting our location to unknown intelligences. For Voyager, Sagan wanted something more ambitious, not a plaque, a record. An actual phonograph record that could be played, containing sounds, music, images encoded in analog format, greetings in multiple languages, a message that represented all of humanity. NASA gave him 6 weeks. Sagan assembled a small team. One of them was a young woman named Ann Druyan, 27 years old, a writer and filmmaker with a passion for science and art and the intersection between them. She had worked with Sagan before, respected his vision, shared his belief that this mission, these 2 spacecraft leaving the solar system forever, deserved to carry something beautiful. Something that said, we were here, we lived, we tried to understand, and we loved. The team worked frantically, choosing sounds, thunder wind of mother kissing her baby, the rumble of a rocket launch, the tapping of Morse code, the song of a humpback whale. Choosing music, Bach's Brandenburg Concerto No. 2, a Navajo night chant, a Pygmy Girl's initiation song, from Zaire Chuck Berry's Johnny Be Good. They wanted to include the Beatles' Here Comes the Sun. EMI, the record label, refused permission. For interstellar distribution. Anne had laughed when she heard that, a bitter, exhausted laugh. We can send music to aliens, she said, but we cannot use the Beatles. It remains one of the more absurd footnotes in the history of intellectual property law. But then Anne had an idea, a strange idea, an idea that had no obvious scientific value but felt to her profoundly important. They should include human brain waves, not thoughts you cannot record thoughts, but the electrical activity of a functioning human brain, an EEG recording, compressed and encoded onto the record, a pattern of neural firing that represented someone thinking, feeling, being alive. She volunteered herself. On June 3, 1977, Anne sat in a laboratory at New York University with electrodes attached to her head. A technician monitored the EEG machine. For 1 hour, she meditated on a prepared list of topics: the history of Earth, the evolution of life, the nature of human civilization, what it feels like to be alive, what it means to love. What the technician did not know, what Anne did not tell anyone except Carl Sagan, was that just 2 days earlier, on June 1st, she and Carl had confessed their love for each other over the phone. They had known each other for years, worked together, respected each other, but something had shifted. Some barrier had fallen, and in a phone call that stretched past midnight, they had both admitted what had been building between them: love. So when Anne sat in that lab on June 3rd meditating on what it means to be human, she was not thinking abstractly. She was thinking about Carl, about the feeling in her chest when she heard his voice, about the way time seemed to stop when they talked about the stars. The brain waves of a woman in love were encoded onto the golden record. No one listening would know. No alien civilization, if one ever found the record, would be able to decode electrical patterns into emotion. But Anne knew. And Carl knew. And somewhere out there in the darkness, traveling at 38,000 miles per hour, a phonograph record made of gold-plated copper carries the neurological signature of human love. It will survive for 1 billion years, long after the sun swells into a red giant and swallows the earth, long after every building, every city, every trace of human civilization has been erased. The record will still be intact, spinning silently in the vacuum, waiting for hands that may never come. Anne is 75 years old now, living in upstate New York. In interviews, when asked about the brainwaves, she says, "I wanted something of our inner life to go with the spacecraft, not just pictures and sounds, but the actual electrical reality of being human." Then she pauses. "And I wanted my love for Carl to be part of it, even if no one else ever knows." The record's lifespan, 1 billion years. Earth has existed for 4.5 billion, which means the golden record will endure for roughly 1/4 of our planet's entire history. Your voice if you had sent a greeting, your laughter, your attempt to say hello across the cosmic distance. It will outlast you, your children, your grandchildren, your civilization. Think about that. A thin copper disc plated in gold enclosed in an aluminum jacket. Instructions for playing it etched on the cover in symbolic language. A needle included for the stylus. And inside, the sound of a human kiss. Thunder, a rocket launching. A baby crying, Beethoven, Chuck Berry, greetings in 55 languages, and the brainwaves of love. August 20th, the rocket climbs. Voyager 2 separates from the upper stage, unfolds its magnetometer boom, a long, delicate arm extending away from the spacecraft body to avoid magnetic interference, unfolds its science platform, points its high-gain antenna toward Earth. The signal arrives at the Deep Space Network, 23 watts, already weakened by distance. But clear, in the control room at JPL, people exhale. Some cry. Some simply stare at the screens showing telemetry data, scrolling past in green monospace text. Eleanor Whitmore, the project scientist, stands near the back of the room, 38 years old, wearing a blazer that was professional in 1965 and now just looks dated. She has been with this mission from the beginning. Through the Grand Tour's death and resurrection, through the budget fights and the compromises and the late nights recalculating trajectories. She does not cheer, does not smile, just watches the data, confirming, verifying. Someone asks her, "How does it feel?" She thinks about that, then says, "Ask me in 12 years. 16 days later, Voyager 1 launches. Perfect descent, perfect separation, perfect signal acquisition. Both spacecraft are now climbing out of Earth's gravity well, accelerating toward the asteroid belt, toward Jupiter, toward destinies that will not fully reveal themselves for decades. Marcus Aldridge goes home that night. His wife is asleep. He pours himself 2 fingers of whiskey, something he almost never does, and sits in his backyard looking up. He cannot see the spacecraft. They are already too far, too small. Just metal boxes coasting through the black on trajectories he calculated 12 years ago when he was 28 and idealistic and believed that solving the math was the hard part. Now he knows the math was easy. The hard part is everything else. The politics, the budgets, the compromises, the fear that something will break, that the plutonium will fail earlier than predicted, that a micrometeorite will punch through a fuel line, that some unforeseen failure, a blown circuit, a stuck valve, a software bug, will end everything. The hard part is living with the fact that once the spacecraft leave Earth, you can never touch them again, can never repair them, can only send commands and hope they are received, hope they are executed correctly, hope the machines keep working. And yet, they are out there. 2 machines, carrying messages, carrying instruments, carrying the best and strangest and most hopeful parts of humanity into a darkness that does not care. Marcus finishes his whiskey. He thinks, "They will outlast me. They will outlast everyone who built them." And that thought, instead of being sad, feels like the most profound kind of victory. 73 days after launch, Voyager 2 crosses the orbit of Mars. 147 days after launch, both spacecraft enter the asteroid belt. Hollywood movies had prepared the public for this. The asteroid belt was supposed to be a dense field of tumbling rocks, spacecraft dodging and weaving, near constant collisions. The reality, emptiness. The average distance between asteroids in the belt is 600,000 miles. You could fly a straight line through the belt, and never come within visual range of a single rock. The belt is not a wall. It is a very sparse neighborhood where the houses are millions of miles apart. Both Voyagers sail through without incident, without even photographing a single asteroid, because there simply is not one close enough to bother with. Beyond the belt, nothing, just vacuum, just the slow, steady cruise toward Jupiter, 500 million miles away. The spacecraft travel at 38,000 miles per hour relative to the sun, fast by any human standard. But space is so large that this speed feels glacial. Days pass, weeks, months. The distance to Jupiter closes with agonizing slowness. During this cruise phase, engineers test instruments, calibrate sensors, upload software patches. The Deep Space Network tracks the spacecraft constantly. 3 massive antennas, Goldstone in California, Madrid in Spain, Canberra in Australia, positioned around the globe, so at least one always has line of sight. The signal strength from Voyager, even at this relatively close distance, is 20 billion times weaker than the power of a digital watch battery, and yet the antennas hear it. 70-meter dishes, weighing hundreds of tons, pointing at a tiny moving speck of metal coasting through the void, listening to a whisper that has traveled millions of miles and arrives so faint it barely registers above the background hiss of the universe. This is not magic, this is engineering. Daniel Brennan spends his days calculating transmission windows, accounting for the frequency drift in Voyager 2's backup receiver. Every command must be precisely timed and precisely tuned. What happens? Someone asks him if you get the frequency wrong. The spacecraft does not hear the command. And then we send it again with the correct frequency. But what if you do not realize you got it wrong? Daniel looks at them, exhausted, patient. We always realize, because we listen. Every command we send, we wait for confirmation. If we do not hear back, we know something failed. We recalculate. We try again. How many times have you had to recalculate? In 342 days since launch twice. It is terrifying, Daniel says, every single time. But he does not stop, does not quit, does not allow himself to imagine failure. Because the spacecraft are depending on him, on all of them. And machines cannot hope or fear or doubt. They only do what they are built to do. They only follow the commands they receive. The humans, fallible, mortal, exhausted, have to be perfect on their behalf. March 5th, 1979. Voyager 1 reaches Jupiter, 466 days after launch, 550 million miles from home. The spacecraft screams past the giant planet at 35,000 miles per hour, cameras clicking instruments, measuring, recording everything. Jupiter fills the field of view, bands of cream and rust and ochre, swirling in parallel stripes. The Great Red Spot, a storm larger than Earth, raging for at least 300 years, dominates the southern hemisphere. Not a simple oval, a churning, layered vortex with smaller storms being pulled into its edges and devoured. The images arrive at JPL hours later. Traveling at the speed of light, engineers crowd around monitors. Scientists stand with mouths open. Some cannot form words, because this is not the Jupiter they expected. Textbooks had shown a few broad bands, relatively stable, simple. This is chaos, beautiful structured chaos, turbulence in layers, eddies within eddies, white ovals, brown barges of descending air. Lightning on the night side thousands of times more powerful than any lightning on Earth. The atmosphere is mostly hydrogen and helium, but trace amounts of ammonia, methane, water vapor create the riot of color. One researcher will later describe it as, someone stirred a pot of butterscotch and forgot to turn off the stove for 3 centuries. Not peer-reviewed language, but accurate. But Jupiter itself is not the revelation. The revelation is the moons. Jupiter has over 90 known moons today. Most are tiny captured asteroids, but 4 are large enough to be worlds in their own right. The Galilean moons, named after Galileo Galilei, who spotted them through his telescope in 1610 and promptly got in trouble with the Catholic Church for suggesting they orbited Jupiter rather than Earth. Io, Europa, Ganymede, Callisto. Voyager's cameras turn toward them, and the universe changes. Io appears first. It is supposed to be dead, cratered, cold, like most moons. Instead, it looks like a burnt pizza. Splotchy oranges, yellows, blacks, whites. Almost no impact craters, which is impossible. Craters accumulate over billions of years. If a moon has no craters, something is erasing them. Something is resurfacing the entire moon. But what a young navigation engineer named Linda Morabito is examining images after Voyager's closest approach. 26 years old, one of the few women in a control room dominated by men. She has learned to spy carefully, to triple-check her work before saying anything, because being wrong even once means months of dismissed ideas and condescending explanations. She is looking at an image of Eo's limb, the edge of the moon against the black of space, and she sees something, a plume, rising above the surface, umbrella-shaped, enormous. She stares at it, runs the image through enhancement, checks for artifacts, for glitches, for anything that might explain it away. The plume is real. She walks to the senior scientist's desk, shows him the image. What is this? He glances at it. Artifact, ignore it. I do not think it is an artifact. Why not? Because it has structure, symmetry, and I can see it in multiple frames. He looks again, frowning now, takes the image, studies it more carefully, then stops. That is, he pauses. That is a volcano, an active volcano. Linda nods. Calm on the outside, screaming on the inside. Yes, the room goes quiet. Because before this moment, Earth was the only known body in the solar system with active volcanism. The only place where geology was not frozen, not dead. Io has 8 active volcanoes, sulfur and sulfur dioxide plumes shooting 200 miles into space. The surface is constantly renewed, constantly resurfacing, erasing craters as fast as impacts can form them. The energy source tidal heating. Jupiter's immense gravity combined with the gravitational tugging of the other large moons flexes Io's interior, kneading it, like squeezing a rubber ball over and over. The friction generates heat, melts rock, powers volcanoes. Scientists had actually predicted this mechanism in a paper published just weeks before Voyager arrived. But prediction and observation are different things. Theory and reality are different things. Seeing actual fire from another world changes everything. Linda calls her mother that night, an Italian immigrant who cleaned houses to put Linda through college. Mama, she says, I found volcanoes, on a moon, on another world. Her mother, who does not fully understand orbital mechanics or spacecraft or interplanetary exploration, understands this. Her daughter discovered something no one else had seen, and that is enough. Europa appears next in Voyager's cameras, a moon completely different from Io. Its surface is a shell of water ice crisscrossed with reddish-brown cracks that make it look like a hard-boiled egg dropped on a kitchen floor. There are very few craters here too, which suggests a young active surface. Something is resurfacing Europa as well, though more gently than Io's violent volcanism. The cracks hint at something moving beneath the ice. Scientists examine the data, the magnetic field measurements, the way Europa interacts with Jupiter's powerful magnetosphere, and they begin to suspect something extraordinary. Beneath Europa's frozen crust, perhaps 10 to 15 kilometers of ice, lies a global ocean, liquid water, kept warm by the same tidal heating that powers Io's volcanoes but gentler, enough to melt ice into water, not rock into magma. Voyager's instruments are not sensitive enough to confirm it directly, but the evidence is compelling. The induced magnetic field, the young surface, the crack patterns. Eleanor Whitmore examines the data in her office, 40 years old now, 2 years into the mission. She has seen things no human has seen before. Jupiter's storms, Io's fire, and now this, a moon that might harbor more liquid water than all of Earth's oceans combined, hidden beneath kilometers of ice, warmed by gravitational forces, protected from radiation by the ice shell above. Liquid water, one of the key ingredients for life as we understand it. She writes in her mission log, "We came to study geology. We may have found biology's next frontier. Europa will eventually become one of the most tantalizing targets in the search for extraterrestrial life. Future missions will be planned. Europa Clipper, possible landers, submarines that could drill through the ice and explore the ocean below. But that is decades away. For now, Voyager gives us just enough to dream about it." Ganymede, the largest moon in the solar system, bigger than the planet Mercury, reveals a surface split between ancient dark terrain and younger grooved light terrain. Evidence of tectonic activity in its past, a moon that was once geologically active and has since quieted. Callisto, the outermost Galilean moon, is the opposite, heavily cratered, ancient, a surface that appears to have changed very little in 4 billion years. A museum piece floating in orbit around a planet that devours storms for breakfast. 4 months later, Voyager 2 arrives at Jupiter, confirms the findings, adds more detail, discovers 2 more volcanoes on Io, maps the moons with different lighting angles. But Voyager 1 is already moving on, already accelerating towards Saturn, using Jupiter's gravity like a slingshot. stealing a fraction of the planet's orbital momentum, gaining 35,000 miles per hour of additional velocity. No rocket engine could provide that kind of boost. But gravity is free. Gravity does not care about budgets or fuel or politics. Gravity just pulls. And if you understand the math, if you can calculate the trajectory precisely enough, you can use that pull to fling yourself across the solar system. Marcus Aldridge, watching the trajectory data, allows himself a small smile. 12 years ago, he had calculated this on a chalkboard at 2 in the morning. And now it is happening exactly as predicted. The math worked. The machines are following the path he drew for them, and there ahead in the darkness is Saturn. November 12, 1980. Voyager 1 approaches Saturn, 900 million miles from Earth, 3 years and 2 months after launch. The rings resolve in the cameras, first as broad bands, then as something infinitely more complex. Not 7 distinct rings, thousands. Ringlets nested inside one another, separated by gaps of varying width. Some gaps contain faint material that should not be there according to models. The rings are not solid. They are vast, flat sheets of ice and rock particles, ranging in size from grains of sugar to houses, all orbiting Saturn in an impossibly thin plane. The ring system spans 170,000 miles in diameter, but it is only 30 feet thick in most places. If you scaled the rings down to the size of a football field, they would be thinner than a razor blade, not a metaphor. Geometry. Voyager discovers structures no one predicted. Spokes, dark radial features that rotate with the rings and seem to defy orbital mechanics. They appear and disappear over hours. The leading explanation, tiny charged particles levitated above the ring plane by electromagnetic forces. Scientists argue about this. Still argue, 45 years later. Shepherd moons appear in the images. Tiny, some no bigger than a city orbiting within and alongside the rings. Their gravity sculpts sharp edges, maintains gaps that would otherwise blur and fill in. One moon pan sits inside the inky gap. It has a distinctive ridge around its equator that makes it look like a ravioli, though that description will not become famous until the Cassini mission photographs it decades later. But the rings are not why Voyager 1 is here. Voyager 1 is here for Titan. Titan is Saturn's largest moon, the only moon in the solar system with a dense atmosphere, thicker than Earth's, composed mostly of nitrogen with a haze of organic compounds that give it a smooth, opaque orange appearance. From a distance, Titan looks like a fuzzy peach. Up close, it still looks like a fuzzy peach, but a fuzzy peach hiding something. Scientists desperately want to know what lies beneath that haze, what the surface looks like, what the atmospheric chemistry is, whether Titan could teach us anything about early Earth before life arose. To get those answers, Voyager 1 must fly close, very close. But here is the problem. Flying close to Titan means the spacecraft's trajectory will be bent sharply by Titan's gravity. Deflected upward, out of the ecliptic plane, the flat disk where all the planets orbit. Once that happens, Voyager 1 will never visit another planet. No Uranus, no Neptune. The grand tour for Voyager 1 ends at Saturn. Marcus Aldridge sits in a conference room at JPL with Eleanor Whitmore and a dozen other scientists and engineers. They have been debating this for months, running simulations, calculating trade-offs. The choice is binary Titan close approach. Invaluable science about atmospheric chemistry, but no Uranus or Neptune. Or skip Titan. Continue to Uranus and Neptune. Complete the grand tour. Eleanor speaks first, 41 years old now. 4 years into the mission, hair beginning to gray. Reading glasses she did not need when the mission started. Titan's atmosphere contains complex organic molecules. Methane, ethane, hydrogen cyanide, chemistry that may resemble early Earth. We may never get another chance to study this up close. Someone else. But the grand tour of Voyager 2 can complete the grand tour. Silence. Voyager 2's backup radio, Marcus says quietly, has been drifting for 3 years. We have compensated perfectly so far. But Uranus is 5 years away. Neptune is 9. Can we guarantee the radio will still function? Can we guarantee we will still be able to compensate for the drift? Eleanor looks at him. No, we cannot guarantee anything. Then we make a choice. We divide the mission. Voyager 1 studies Titan and leaves the solar system plane. Voyager 2 continues to Uranus and Neptune. Marcus thinks about this. Thinks about 12 years of dreaming about visiting all 4 giant planets with both spacecraft. Thinks about the grand tour as he originally imagined it. Then he thinks about Titan. about organic chemistry frozen in time, about an atmosphere that might hold clues to how life began on Earth. Titan, he says. Voyager 1 goes to Titan. The vote is unanimous. November 13th, 1980, Voyager 1 swoops past Titan. Cameras peer through the haze, cannot see the surface but measure the atmospheric composition. Temperature, pressure. The surface pressure is 1.5 times Earth's. You could stand on Titan without a pressure suit. You would freeze solid in the negative 290-degree cold, and you would suffocate in the nitrogen atmosphere, but you would not explode from vacuum. So that is something. The gravity is low, the atmosphere is thick, which means if you strapped wings to your arms, you could fly by flapping. This is real physics, not speculation. Though no human will ever test it, Voyager 1 completes the flyby. The gravitational deflection occurs exactly as calculated. The spacecraft's trajectory bends upward. Out of the plane, climbing, it will never see another planet. Behind it, Voyager 2 approaches Saturn on a different path, a path designed to preserve its ability to reach Uranus and Neptune. The twins have diverged. One climbs, one runs forward, and the Grand Tour Impossible canceled, resurrected, disguised, executed continues, but only for one of them. August 25th, 1981. Voyager 2 reaches Saturn, confirms what its twin discovered 9 months earlier. The rings, the spokes, the shepherd moons, the complexity that makes textbook diagrams look like children's drawings. But Voyager 2 does not linger at Titan. Its trajectory is carefully designed. Precise. A path that threads between Saturn's moons and uses the planet's gravity to fling the spacecraft outward on a new heading, northeast, toward a pale blue-green dot 4 years away. Uranus. No spacecraft has ever been there. No telescope on Earth has ever resolved more than a featureless disk. Scientists know it exists, know its mass, its orbit, its approximate size. But what it looks like up close, what its moons are like, what secrets it might hold, unknown. Voyager 2 begins the longest solo cruise in the history of space exploration. 4.5 years, nothing to photograph, nothing to study, just darkness, just the slow, patient coast through empty space. The plutonium continues to decay. Predictable, unstoppable. The power output drops by 4 watts per year. Slow, inevitable. Instruments are turned off to conserve energy. Heaters are disabled. The spacecraft grows colder. Components operate at temperatures well below their design specifications, and somehow they keep working. Daniel Brennan continues to track the frequency drift of the backup radio receiver. Every day, every command, calculating, compensating. 32 years old now. 5 years into a mission that was supposed to last 5 years total. He is no longer the youngest person in the control room, but he is still the one who understands Voyager 2's dying radio better than anyone. Eleanor Whitmore coordinates the science planning. What instruments to keep active? What data to collect during the cruise? How to prepare for Uranus? And in Pasadena at the Jet Propulsion Laboratory, a software engineer named Evelyn Katz begins working on a problem that seems impossible. Uranus is twice as far from the sun as Saturn, which means it receives 1/4 the sunlight, which means Voyager's cameras designed for the brightness of Jupiter and Saturn will be taking pictures in near darkness. Long exposures will be required, multiple seconds per image. But the spacecraft is traveling at 40,000 miles per hour. Long exposures while moving that fast produce blurred images, streaks instead of detail. Unless the spacecraft can rotate slowly during the exposure, tracking the target, compensating for its own motion, like a photographer panning to follow a moving subject. But Voyager was not designed to do this. The flight software does not include this capability. Evelyn is 34 years old. She has been writing software for spacecraft since the early 1970s. Mariner missions, Viking landers, now Voyager. She sits at her desk with printouts of Voyager's flight software. 69 kilobytes of memory, written in assembly language, every byte precious, every instruction optimized. And she needs to add a new capability without breaking anything that already works. She writes the code, tests it on ground simulators, debugs it, verifies it, and then uploads it to a spacecraft 1 billion miles away, across a signal that takes 90 minutes to travel one way. The upload takes months. The testing takes months more. And it works. Voyager 2, designed and built in the 1970s with memory smaller than a single email, has been taught a new skill, remotely, across distances that make the mind stumble. Evelyn will later say when she's in her 60s and retired, "We fixed a spacecraft we could not touch, across a distance we could barely comprehend. And it did exactly what we asked. Perfectly. She pauses. That spacecraft trusted us, and we earned that trust. January 24th, 1986. Voyager 2 arrives at Uranus. The planet appears in the cameras, pale, featureless, blue-green like a faded swimming pool in winter. A uniform aquamarine tint with almost no visible cloud structure, compared to the riotous bands of Jupiter and the elegant cream of Saturn-Uranus, looks almost boring. Scientists are initially disappointed. Then the instruments start returning data, and the weirdness begins. Uranus is tipped on its side, 98 degrees. Its rotational axis is nearly parallel to its orbital plane, which means the planet essentially rolls around the sun like a ball instead of spinning like a top. No one knows for certain why. The leading hypothesis, a massive collision early in the solar system's history, an Earth-sized object slamming into Uranus with enough force to knock it sideways. One catastrophic impact or multiple smaller collisions. The debate continues. No consensus. At the time of Voyager's visit, the planet's south pole is pointed almost directly at the sun, which means one hemisphere has been in continuous sunlight for decades, while the other has been in continuous darkness. The magnetic field is equally strange. On Earth, the magnetic field is roughly aligned with the rotational axis, North Pole, near the magnetic North Pole. Simple, sensible. Uranus's magnetic field is tilted 60 degrees from the rotational axis and offset from the planet's center, as if someone installed the magnet crooked and forgot about it. This creates a corkscrew-shaped magnetotail that spirals behind the planet as it moves through the solar wind, unlike anything seen at Jupiter or Saturn. Eleanor Whitmore stares at the data, 47 years old now, 9 years into the mission. She has seen Jupiter's storms, Io's volcanoes, Saturn's rings, Titan's haze, and now this, a planet lying on its side with a crooked magnetic field. This does not make sense, she says. Which part? All of it. But the real surprises are the moons. Voyager discovers 10 new moons, bringing the known total to 15 at the time. The 5 largest, Miranda, Ariel, Umbriel, Titania, Oberon, have surfaces that tell stories of violence and chaos. Miranda is the star, the smallest of the 5 major moons. Only 300 miles across. It should be a simple cratered ball, dead, frozen. Instead, its surface is a nightmare. Patchwork terrain, huge chevron-shaped features. Towering cliffs up to 12 miles high, 3 times the height of Mount Everest. Grooved regions sitting next to heavily cratered plains. It looks like a moon that was smashed apart and then reassembled by someone who did not care if the pieces matched. One hypothesis, Miranda was indeed shattered by a massive impact. Gravity pulled the pieces back together. The different terrain types are fragments from different depths jumbled together. Another hypothesis, internal geological processes. Cryovolcanism, tectonic activity driven by tidal heating, created the chaos without any shattering. No consensus. 40 years later, scientists still argue. Miranda remains one of the most visually bizarre objects in the solar system, a jigsaw puzzle where the pieces are from different boxes. Voyager 2 completes its flyby, uses Uranus's gravity for one more boost, one more course change. Destination Neptune, 3.5 years away. During the cruise to Neptune, something happens that no one anticipated. The mission budget is running out. Voyager was supposed to end at Saturn. The extension to Uranus was approved grudgingly. The extension to Neptune, the farthest planet, the most expensive operation, the longest communication delay, faces opposition. Congress is skeptical. Why spend money photographing empty ice balls? NASA's budget is tight. The shuttle program demands resources. Space station freedom is in planning. There is genuine risk that Voyager 2 will be shut down before reaching Neptune. Eleanor Whitmore testifies before Congress, 50 years old now. Graying hair pulled back, reading glasses perched on her nose. We have a spacecraft, she says, that has traveled for 12 years, that has visited Jupiter, Saturn, and Uranus, that is functioning perfectly despite being designed for a 5-year mission. That is now 3 years from Neptune, a planet no human will visit in our lifetimes, possibly ever. She pauses. Turning it off now would be like climbing Everest and stopping 10 feet from the summit because you are tired. One senator asks, what scientific value does Neptune have? Eleanor looks at him. We do not know. That is the point. We do not know what we will find. But every time Voyager has visited a new world, it has discovered something that changed our understanding. Io's volcanoes, Europa's ocean, Miranda's chaos. Every single time the universe surprised us. That is not a guarantee. No, but exploration never comes with guarantees. Only possibilities. The funding is approved. Barely. Voyager 2 continues toward Neptune. August 25, 1989. 12 years after launch. 4 billion miles from Earth. Signal delay 4 hours round trip. Voyager 2 approaches Neptune, and Neptune is nothing like Uranus. Where Uranus was pale and featureless, Neptune glows a deep, rich sapphire blue. Vivid, saturated, the most intensely colored planet in the solar system. The atmosphere is alive with features. A massive storm in the southern hemisphere, quickly dubbed the Great Dark Spot, roughly the size of Earth, ringed by bright white clouds of methane ice crystals that race along its edges at staggering speeds. The winds on Neptune exceed 1,200 miles per hour, the fastest ever recorded on any planet in the solar system. This makes no sense. Wind is driven by energy. On Earth, the sun heats the equator more than the poles. Temperature difference drives circulation, drives weather. Neptune receives 1/900th of the sunlight Earth does. It should be dead, calm, frozen. Instead, it has the most violent weather in the solar system. Something internal must be driving the winds, residual heat from the planet's formation perhaps, or ongoing gravitational contraction. The exact mechanism remains unknown. Scientists still argue. A smaller storm appears in the images, nicknamed Scooter for the speed at which it races around the planet, and another dark spot farther south. The atmosphere is layered, complex, bands and vortices interacting in ways that atmospheric modelers will spend decades trying to reproduce. But here is the strange thing. When the Hubble Space Telescope looks at Neptune 5 years later, the great dark spot is gone, vanished. Neptune churns through storms the way you churn through streaming subscriptions, rapidly, unpredictably, with no apparent loyalty. Eleanor watches the images arrive, storm after storm, wind measurement after wind measurement, 50 years old, 12 years into a 5-year mission. We expected ice, she says quietly. We found fury. But Neptune itself is not the revelation. The revelation is Triton. Triton is Neptune's largest moon, and immediately something is wrong with it. It orbits backward, retrograde, opposite to Neptune's rotation. This is not how moons behave. Moons that form alongside their planets orbit in the same direction the planet rotates. Always, without exception, unless they did not form there, unless they were captured. The leading theory, Triton was once a Kuiper Belt object, a distant icy body orbiting the sun independently, similar to Pluto, wandering too close to Neptune and snared by its gravity. If true, Triton is essentially Pluto's cousin, kidnapped and forced into servitude around a giant planet. The surface confirms this. Triton is covered in nitrogen and methane ice, a pinkish hue from organic compounds created by ultraviolet radiation breaking down methane. The terrain includes bizarre features nicknamed cantaloupe terrain, a vast region of roughly circular dimples and ridges that looks exactly like the skin of a cantaloupe melon. No one is entirely sure how it formed. There are frozen lakes of refrozen nitrogen, long cracks, smooth plains that suggest relatively recent geological activity. The surface temperature is negative 391 degrees Fahrenheit, the coldest measured surface of any solid body visited by a spacecraft. And yet, Triton is not dead. Voyager's cameras captured dark plumes rising from the surface, geysers, nitrogen gas erupting through the ice and shooting material up to 5 miles into the thin atmosphere before the wind carries it downwind in long, dark streaks across the frozen surface. Cryovolcanos. Volcanism powered not by molten rock, but by solar heating of subsurface nitrogen ice that vaporizes and blasts through weak spots in the crust. It is volcanism turned inside out. Frozen volcanism on a frozen world. And it is happening in real time as Voyager flies past. The discovery of active geology on a moon this cold, this far from the sun, changes everything, because it demonstrates that geological activity does not require proximity to a star. Energy can come from tidal forces, from residual heat, from the simple physics of ice under pressure. The solar system is far more alive than anyone imagined in 1977. Eleanor sits in the control room at JPL watching the images arrive. Geysers on a moon where the temperature makes liquid nitrogen impossible, where the sun is a dim star barely brighter than others. And she thinks, we almost did not come here. We almost turned the spacecraft off. The vote in Congress had been close, and now they are seeing something no human expected. Something that will change the way we think about where life might exist, about what habitable might mean. Voyager 2 completes the Neptune flyby, uses the planet's gravity for one final acceleration, but this time there is no next destination. The trajectory bends downward, below the ecliptic plane, heading south and outward. The grand tour is complete. Every giant planet visited. Jupiter, Saturn, Uranus, Neptune, moons discovered, rings analyzed, magnetic fields mapped, atmospheres measured, 48 new moons added to the solar system's inventory, volcanism discovered beyond Earth, subsurface oceans inferred, weather patterns that break all models, geology on the coldest worlds. Voyager 2 has accomplished everything the Grand Tour promised. And more. In the control room, people cheer, cry, embrace. Eleanor Whitmore stands quietly near the back, 50 years old, 12 years with this mission. Someone asks her, how does it feel? She thinks about that question, the same question she was asked 12 years ago. Ask me, she says, in another 12 years. Because the journey is not over. Both Voyagers are still out there, still transmitting, still measuring, and ahead, far ahead, farther than any planet lies something else. The edge of everything we know. February 14th, 1990, Valentine's Day. Voyager 1 is 3.7 billion miles from Earth. Its planetary mission has been over for nearly a decade. The cameras have been idle. The spacecraft coasting silently through a region of space where there is nothing to photograph. And then a command arrives from Earth, traveling at the speed of light, taking 5.5 hours to reach the spacecraft. The command tells Voyager 1 to do something it was never designed to do. Turn around, point the camera back toward home, take one last picture. This is Carl Sagan's idea. He has been lobbying NASA for years to use Voyager's camera to capture a portrait of the solar system from the outside, a family photo taken from the porch of the sun's most distant territory. Many at NASA resist. The images will have no scientific value. The planets will be tiny specks barely distinguishable from background noise. Pointing the camera back toward the sun risks damaging the imaging system, and the bandwidth required to transmit the images will take time away from other data. But Sagan persists, with the quiet, relentless charm that made him one of the most persuasive scientists of his generation. NASA agrees. Voyager 1 rotates its scan platform, takes 60 frames, a mosaic of the inner solar system, capturing 6 of the 9 recognized planets. Mercury is too close to the sun to distinguish. Mars is lost in scattered sunlight. Pluto is too small and too dim. But Venus, Earth, Jupiter, Saturn, Uranus, and Neptune are all there. Tiny points of light suspended in beams of scattered sunlight that streak across the frames like theatrical spotlights on the emptiest stage imaginable. One frame in particular will become one of the most famous photographs in human history. In it, Earth appears as a tiny pale blue dot, less than a single pixel in size, caught in a band of scattered light that makes it look like a mote of dust floating in a sunbeam. The image is not beautiful in any conventional sense. It is grainy, washed out. If you did not know what you were looking at, you would see nothing meaningful at all. But Carl Sagan looks at it and sees everything. He writes about it, a passage that will be quoted for generations. Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor, and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. He does not say these things to make you feel small. He says them to make you feel connected to every other human, to the planet itself, to the improbable chain of events that led to you existing at all. The pale blue dot image is not science. It is philosophy delivered by a camera with 1970s optics from the edge of the known world. Anne Druyan is 69 years old when she reflects on this photograph in 2019. She sits in her home office, pictures of Carl on the walls. He died in 1996, too young, too soon. When I see that image, she says, I think about the brainwaves on the golden record. My brainwaves, my love for Carl. She pauses, eyes distant. All that love, all that hope, all those feelings, they came from that tiny dot, and now they are out there, beyond that dot, traveling through the cosmos. Another pause. Carl used to say the cosmos is within us. We are made of star stuff. But looking at that image, I think we are also the cosmos looking back at itself. That pale blue dot learned to build machines, to send them across billions of miles, to turn around and see itself. She touches the image on her desk. And to love. Do not forget that. The dot learned to love. After the mosaic is complete, Voyager 1's cameras are turned off permanently. To conserve power, the spacecraft will never take another photograph. From this point forward, it sees the universe only through its instruments. Magnetometers, plasma sensors, cosmic ray detectors, tools that measure the invisible. You might find that sad, losing the ability to see. But the spacecraft does not experience sadness. It simply continues doing what it was built to do, gathering data in the dark. The 1990s pass. Both Voyagers coast outward. Voyager 1 heading north and east, Voyager 2 heading south and east, different directions, different speeds, bound for different patches of interstellar space. The distance between them grows. They will never meet again. On Earth, the team managing Voyager shrinks. Budget cuts, retirements, younger engineers moving to newer missions. The Voyagers are old news, ancient technology, spacecraft from a different era. But a small, dedicated group remains. Eleanor Whitmore, now in her 50s and 60s, still the project scientist, still coordinating, still planning. Daniel Brennan, now in his 40s and 50s, still calculating frequency drift, still sending commands, still listening. Evelyn Katz, now in her 40s and 50s, still writing software patches, still uploading fixes across billions of miles. And newer engineers, younger, born after the Voyagers launched, learning from the veterans, taking over responsibilities as the older generation ages. The plutonium continues to decay, predictable, unstoppable. Power output drops by 4 watts per year. Instruments are turned off one by one. The ultraviolet spectrometer off, the infrared spectrometer off, various heaters off. The spacecraft grow colder. Components operate at temperatures well below their design specifications. And somehow they keep working. The public forgets about Voyager. The media stops covering it. There are no new images, no dramatic flybys, just 2 old spacecraft coasting through empty space, transmitting data that only a handful of specialists understand. But that data is building something, a map. Not a map of where things are, a map of what space is like, out there, beyond the planets, in the region where the sun's influence starts to fade. Because Voyager is approaching something, a boundary, the edge of everything. 2002. Voyager 1 is 90 astronomical units from the sun. 1 astronomical unit equals the distance from Earth to the sun, 93 million miles. 90 astronomical units is 8.4 billion miles. The spacecraft's instruments begin detecting anomalous readings. The intensity of certain low-energy charged particles, anomalous cosmic rays, starts to increase. These particles are thought to originate from interstellar neutral atoms that have been ionized and accelerated at a boundary ahead. The magnetic field fluctuations become more erratic, more turbulent. Something is changing in the environment around the spacecraft. Some scientists believe Voyager 1 has crossed the termination shock, the boundary where the solar wind, the constant stream of charged particles flowing outward from the sun, slows from supersonic to subsonic speeds. A team led by Stamatios Kremigas publishes a paper arguing exactly this. Based on particle data from 2002, other teams disagree. They argue that the particle enhancements could be caused by a transient event, a burst of solar activity propagating outward, not a permanent crossing of the shock boundary. The debate becomes heated, which in astrophysics means sharply worded peer-reviewed papers rather than raised voices, but sharp enough to leave marks. The confusion arises partly because the termination shock is not static. It breathes. When the sun is more active, pumping out stronger solar wind, the shock is pushed farther out. When the sun quiets down, the shock contracts inward. It is entirely possible for the shock to wash over a spacecraft and then retreat, crossing you and then uncrossing you, like a wave lapping at your feet on a beach. Scientists still argue whether Voyager 1 experienced one or more of these back-and-forth crossings in 2002 and 2003, a dance with a boundary that refused to hold still. The definitive crossing comes in December 2004, approximately 94 astronomical units from the sun. Voyager 1's magnetometer detects a sudden increase in magnetic field strength, the compression you would expect as the solar wind slams to a halt and piles up against itself. The cosmic ray intensity jumps. The character of the particle environment changes in a way consistent with the spacecraft now sitting in slower, hotter, turbulent plasma downstream of the shock. This time, most of the scientific community agrees. Voyager 1 has crossed the termination shock, entered the heliosheath, the thick, turbulent region between the shock and the outer edge of the heliosphere. Eleanor Whitmore is 65 years old, still working, still coordinating, 27 years into a 5-year mission. When asked about the crossing, she says, "We are in the buffer zone, not outside, not yet, but closer." How much closer? Years, maybe a decade. The heliosheath is thick. We are measuring it for the first time, learning what it is, where the true edge lies. She pauses. Patience. We have come this far. We can wait. The heliosheath is not what anyone expected. For years, the standard picture was relatively simple. The solar wind slows down, gets compressed, flows along the inside of the heliopause, the true outer boundary, and eventually drains away into the tail of the heliosphere behind the sun. The magnetic field was expected to be fairly smooth, draping over the heliosphere in long, graceful arcs. A tidy picture, the kind that looks great in textbooks. Voyager destroys it. Starting around 2007, Voyager 1's magnetometer begins detecting something odd. The magnetic field in the heliosheath is not smooth. It is frothy. The field direction fluctuates wildly over short distances, suggesting the plasma is organized into distinct magnetic structures. Bubbles, each one roughly 100 million miles across. A team led by physicist Merav Ofer proposes that the sun's magnetic field, which reverses polarity every 11 years, as part of the solar cycle, creates alternating sectors of positive and negative magnetic polarity in the solar wind. When this sectored wind reaches the heliosheath and gets compressed and turbulent, those alternating sectors break up into a foam of magnetic bubbles, a cosmic bubble bath. Each bubble a self-contained magnetic island with its own field direction, jostling against its neighbors in a slow, churning dance. This discovery matters far more than it might seem. The heliosheath is the solar system's last line of defense against galactic cosmic rays, high-energy particles from exploding stars and other violent events elsewhere in the Milky Way. Scientists had assumed the smooth magnetic field would act as a coherent shield, deflecting incoming cosmic rays the way a curved windshield deflects rain. But a foam of disconnected magnetic bubbles works very differently. Instead of deflecting cosmic rays in an organized way, the bubbles scatter them, sometimes trapping them temporarily, sometimes letting them through. The shielding effect is real but messier and less predictable than models assumed. This has implications for future human space travel beyond the heliosphere, because the intensity and behavior of cosmic radiation in this region determines how much shielding a crewed spacecraft would need. The answer, courtesy of Voyager, probably more than we thought. Daniel Brennan is 62 years old, still tracking Voyager 2's frequency drift, still sending commands, 30 years into the mission. Someone asks him, "After all these years, does it ever get routine?" He looks at them, surprised by the question. Routine, we are listening to a machine 8 billion miles away, measuring magnetic bubbles in a region no human has ever imagined visiting, compensating for a broken radio that has been drifting for 30 years. He pauses. Nothing about this is routine. Every command is a small victory. Every response is a gift. And the commands keep going. And the responses keep coming. 160 bits per second, slower than a 1960s modem, but sufficient. The data arrives. Scientists analyze it, argue about it, publish papers, refine models. And Voyager 1 continues outward, towards something ahead, something the magnetic bubbles and particle intensities and field fluctuations all suggest is there. The heliopause, the true edge, the boundary between everything we have ever known and everything else. July 28, 2012. Voyager 1 is 121 astronomical units from the Sun, 11.3 billion miles. The signal takes 17 hours to reach Earth, traveling at the speed of light. The cosmic ray detectors register a dramatic change. The intensity of galactic cosmic rays, those high-energy particles originating from outside the solar system, begins to climb sharply. Within days, the count rate increases by nearly 10%. Simultaneously, the intensity of lower-energy particles associated with the solar wind begins to drop. It is as if someone is slowly opening a door, galactic radiation flooding in, solar particles draining out. This is broadly what you would expect as the spacecraft approaches the heliopause, the true outer boundary of the heliosphere. But then on August 1st, the readings reverse. Cosmic rays drop back down. Solar particles reappear. The spacecraft has apparently popped back inside the heliosphere. August 5th, the transition happens again. Out and then back in. What Voyager 1 has discovered is a region that no model predicted. They call it the magnetic highway, a zone where the magnetic field lines from the sun appear to connect with the magnetic field lines of the interstellar medium, creating open pathways along which particles can travel freely. Solar particles trapped inside the heliosphere for years suddenly have an escape route. They stream outward along these connected field lines. Galactic cosmic rays previously deflected by the heliosphere's magnetic barrier now have a highway inward. The result is exactly what Voyager observes: a rapid exchange of particles in both directions, two-way traffic on a magnetic road that runs along the boundary of the heliosphere. The magnetic highway is a genuinely new discovery, not in the models, not predicted by any theorist. A boundary layer, a cosmic customs checkpoint where particles are exchanged, but the magnetic architecture has not yet fully changed. And it complicates the already difficult question of when exactly Voyager 1 leaves the solar system. Because here's the problem. If you define the edge by the particle environment where galactic cosmic rays dominate and solar particles disappear, then Voyager crossed during one of those stuttering transitions in late July or early August 2012. But if you define the edge by the magnetic field, where the sun's magnetic field gives way to the interstellar magnetic field with a different direction and possibly different strength, then Voyager has not crossed yet. Because the magnetic field in the highway region still looks solar in character. Scientists argue, papers are published, conferences held. The debate reveals something humbling. Even after traveling 11 billion miles, we are not entirely sure how to draw the line on a map. Eleanor Whitmore is 73 years old, watching the data, listening to the arguments, 35 years into the mission. We thought, she says to a colleague, that the boundary would be simple, a line. You cross it or you do not. And the universe is teaching us once again that simple is for textbooks. Reality is complicated. The stuttering crossings continue through August. Each time Voyager dips into the region of enhanced cosmic rays and depleted solar particles, it stays there for a few days before bouncing back. The simplest explanation, the heliopause itself, is not static. It ripples and undulates in response to changes in solar wind pressure and interstellar medium pressure. Like a flag in gusty wind, the boundary washes back and forth across Voyager's position, and the spacecraft alternately finds itself on one side and then the other. A cosmic game of tug-of-war, and Voyager is sitting right on the rope. Then on August 25, 2012, the cosmic ray intensity rises one final time and stays high. The solar particle count drops and stays low. The magnetic highway has delivered Voyager 1 to the other side. No bounce back. The spacecraft has crossed the heliopause into interstellar space. Except nobody realizes it. Not yet. Not for 13 months. The problem once again is the magnetic field. When Voyager 1 crosses the heliopause, the science team expects to see a dramatic change in the direction of the magnetic field. A rotation from the solar field orientation to the interstellar field orientation. Models predict the interstellar field should point in a significantly different direction, but the magnetometer data shows no such rotation. The field strength changes slightly. The field becomes smoother, more steady, but its direction remains stubbornly close to what it was inside the heliosheath. This is baffling. If the magnetic field has not changed direction, how can you claim the spacecraft has left the heliosphere? Maybe the particle changes are just another temporary fluctuation. Maybe the boundary has shifted again. Maybe Voyager is in some new unknown transition region that nobody has a name for yet. The debate within the science team becomes intense. Eleanor, cautious by nature, is not willing to declare that Voyager has entered interstellar space until the evidence is unambiguous. Others believe the crossing has occurred, but need one more piece of evidence to prove it. Papers are written, reviewed, argued over. The scientific community watches and waits. And then in April 2013, something unexpected happens. A massive coronal mass ejection, a burst of solar plasma hurled outward by an explosion on the sun's surface, reaches Voyager 1's location. After traveling for over a year, when this wave of solar plasma arrives, it causes the plasma around the spacecraft to vibrate, to oscillate at a frequency that Voyager's plasma wave instrument can detect. These oscillations are critical, because their frequency reveals the density of the plasma surrounding the spacecraft. Dr. Donald Gurnett leads the plasma wave team. He has been waiting for this kind of event, an external disturbance that would shake the plasma and reveal its properties. The frequency is measured. The density is calculated, 0.055 electrons per cubic centimeter, roughly 40 times higher than the density of plasma inside the heliosheath. and it matches almost exactly the predicted density of the local interstellar medium. This is the smoking gun. The plasma around Voyager 1 is not solar, it is interstellar. The spacecraft is immersed in the thin, cold plasma that fills the space between stars. The same medium that has existed in this part of the galaxy for billions of years, long before the sun was born. Gurnet's team works backward, using the plasma wave data to pinpoint when the density transition occurred. They arrive at a date, August 25, 2012. Voyager 1 crossed into interstellar space on that date, and nobody knew for 13 months, September 12, 2013. NASA holds a press conference. Eleanor Whitmore stands before cameras, 74 years old now, white hair, reading glasses, the same calm, measured voice she has had for 50 years, 36 years into a 5-year mission. Voyager 1, she says, has become the first human-made object to enter interstellar space. The room erupts, questions shouted, cameras flashing, reporters scrambling. For a brief, shining moment, a spacecraft launched in 1977 with the computing power of a digital watch becomes the most famous machine on, or rather off the planet. The internet lights up. Social media explodes. Front page of every major newspaper. Because this is not just a scientific milestone. This is a human milestone. For the first time in 4.5 billion years of Earth's existence, something made by life on this planet has left the sun's domain entirely. We are outside. Marcus Aldridge is 76 years old, retired, living in a small house near Pasadena. He watches the press conference on television. He thinks about standing in front of a chalkboard in 1965, 28 years old, sketching orbital paths, noticing an alignment. 48 years ago, half a century, and now the machines he helped send are out there, beyond everything, measuring the galaxy from the inside. He does not cry, but his hands shake slightly as he turns off the television. His wife, married 63 years, asks if he is okay. He nods. They made it, he says quietly. They actually made it. Andrion is 64. She hears the news and thinks about June 3rd, 1977. Sitting in a laboratory with electrodes on her head, thinking about Carl, about love. Those brain waves are out there now, beyond the heliopause, in interstellar space. Carl died in 1996, 17 years ago. Too young, 62 years old, bone marrow disease. But part of him is still traveling, his voice on the golden record, his ideas encoded in the selections, his vision of what humanity could be, and her love for him, neural patterns representing emotion. Compressed into analog format, spinning on a golden disc, beyond the edge of everything, she writes in her journal that night, Carl always said we are a way for the cosmos to know itself. Today I understand what he meant. We built machines that left home, that crossed into the true cosmos, and in doing so, we tiny creatures on a pale blue dot became citizens of something larger. But the mystery of the magnetic field lingers. Why did the field direction not change at the heliopause? Scientists still argue over this question. No consensus has emerged. One hypothesis suggests the interstellar magnetic field near the heliopause has been draped and deformed by its interaction with the heliosphere, bending it into an orientation that happens to align with the solar field. Another suggests the heliopause is not a simple boundary, but a more complex structure, a transition layer where fields from both sides intermingle. A third, more radical idea: the models predicting a sharp magnetic rotation were simply wrong. The interstellar magnetic field in the sun's neighborhood points in a direction closer to the solar field than anyone expected. The debate continues. In journals, at conferences, in late-night emails between researchers who have spent decades studying this boundary. And that is okay, because science is not about having all the answers immediately. Science is about asking better questions, refining understanding, admitting uncertainty while still making progress. Voyager 1 is in interstellar space. The particle environment confirms it. The plasma density confirms it. The magnetic field mystery remains. But mysteries are not failures. They are invitations. Invitations to keep looking, keep measuring, keep thinking. Eleanor says it best: we know more than we did, we know less than we will. That is how it should be. November 5th, 2018. 6 years after Voyager 1's crossing, Voyager 2 reaches the heliopause, 119 astronomical units from the Sun, about 2.5 astronomical units closer than Voyager 1's crossing point, but in a completely different direction. Voyager 1 exited the heliosphere heading north, toward the constellation Ophiuchus. Voyager 2 exits heading south, toward the constellation Pavo. The two spacecraft have effectively punched holes in opposite sides of the heliosphere. And the comparison between their readings is invaluable, because this time, Voyager 2 has an advantage. Remember that broken plasma instrument on Voyager 1? The one that failed in 1980? Voyager 2's plasma science experiment is still working. For the first time, a spacecraft crosses the heliopause with the ability to directly measure the speed density and temperature of the plasma on both sides of the boundary. This is the measurement scientists have been craving for decades. The solar wind plasma flowing outward at reduced speeds through the heliosheath drops to effectively zero within a distance of less than 1 day's travel, roughly 1 million miles. Simultaneously, the interstellar plasma appears, denser, cooler, filling the space the solar wind vacated. The transition is remarkably sharp, not gradual. A wall. One moment you are in solar plasma, the next you are in interstellar plasma. And the boundary between them is thinner and cleaner than most models predicted. This sharpness suggests the heliopause is maintained by a strong pressure balance. A taut membrane stretched between the outward push of the dying solar wind and the inward press of the interstellar medium. But here is where the comparison becomes fascinating. Voyager 1's crossing showed those stuttering back and forth fluctuations, the spacecraft dipping in and out of interstellar territory for weeks. Voyager 2's crossing is much cleaner. There is some variability in the days leading up to the transition, but the actual heliopause crossing is a single definitive event. The spacecraft passes through and does not come back. Why the difference, scientists debate, still argue. Perhaps the heliopause is more rippled or unstable in the direction Voyager 1 traveled. Or perhaps it is a temporal effect. The Sun was near solar maximum during Voyager 1's crossing and closer to solar minimum during Voyager 2's. Different solar wind pressure, different boundary behavior. The magnetic field at Voyager 2's crossing behaves similarly to Voyager 1's. Field strength increases slightly, field becomes smoother, but no dramatic rotation in direction. The mystery persists, but now it is confirmed across two widely separated crossing points. The interstellar magnetic field, as measured by both Voyagers, appears to be oriented in roughly the same direction as the solar magnetic field in the outer heliosheath. This consistency strengthens the hypothesis that the interstellar field has been draped and aligned by its interaction with the heliosphere. But it does not definitively rule out other explanations. The magnetic field mystery is not a fluke of Voyager 1's location. It is a feature of the boundary itself. Daniel Brennan is 68 years old. He has been calculating frequency drift for Voyager 2 for 41 years. 41 years. Every command tuned to predict where the backup receiver will be when the signal arrives hours later. Never lost contact. Not once, 14,965 days. Perfect. Someone asks him how he feels about Voyager 2's crossing. He thinks for a long moment. Relieved, he says finally. We kept the connection alive long enough. The spacecraft made it. And now we keep listening for as long as the plutonium lasts. 2017. A graduate student at Cornell University named Stella Ocker is analyzing plasma wave data from Voyager 1. 24 years old. Brilliant pattern recognition. The kind of mind that sees structure in noise. She is looking at the data between solar events, between those occasional coronal mass ejections that cause obvious plasma oscillations. And she notices something. A faint, persistent, narrowband signal. Roughly 3 kilohertz. It is not noise, not an instrument artifact. It is real. The interstellar medium itself is vibrating at a low, steady frequency. A hum, continuous, unrelenting, like the barely audible drone of a refrigerator in a quiet house at 3 in the morning. This interstellar hum is a plasma oscillation, a vibration of the electrons in the interstellar plasma at a frequency determined by the local electron density. The frequency is extraordinarily low, 3,000 hertz, within the range of human hearing. If you could somehow convert the plasma wave directly into a sound wave, though you cannot obviously, it would sound like a faint, thin tone. Not particularly musical, not particularly dramatic, but its significance is enormous, because it provides a continuous real-time measurement of the interstellar plasma density along Voyager 1's path. For this discovery, plasma density could only be measured during sporadic events. Those rare moments when a solar shockwave rattled the interstellar medium and caused detectable oscillations. Between those events, which might be separated by months or years, the plasma density was essentially unknown. The hum fills in the gaps. It is always there, always measurable, always whispering the density of the medium through which Voyager is traveling. And what the hum reveals is that the interstellar medium is not static. The plasma density fluctuates slowly over time and distance, rising and falling in gentle undulations, suggesting the presence of low-frequency waves or turbulence in the interstellar medium. These fluctuations are subtle, changes of perhaps 10 or 20% over periods of months, but they are real. The first direct detection of fine-scale structure in the interstellar plasma. Stella publishes her findings. The paper includes an audio rendering of the plasma wave data, pitch shifted into a comfortable hearing range, time compressed so months of data can be heard in seconds. The result is eerie and beautiful, a low, wavering drone, punctuated by occasional brighter tones when solar events excite the plasma. It sounds like wind blowing across the mouth of a vast empty bottle, or a recording from the bottom of an ocean where no light reaches. Media outlets play the recording. Millions of people hear for the first time the sound of interstellar space. It is not silence out there. It is a hum, faint, persistent, ancient, ongoing, vibrating at a frequency set by the density of matter between the stars, a note that has been playing since long before the sun existed, and will continue long after it is gone. Eleanor listens to the recording in her home office, 78 years old now, mostly retired, still consulting occasionally, 40 years into a 5-year mission. She closes her eyes. She thinks, we did that. Imperfect humans with limited budgets and 1970s technology. We sent machines into the cosmos, and they are still singing back to us, still teaching us, still revealing. 2025. Present day. Voyager 1 is 165 astronomical units from the Sun, 15.3 billion miles. Signal travel time 22 hours at the speed of light. Voyager 2 is 138 astronomical units, 12.8 billion miles. Signal travel time 19 hours. Both spacecraft are still transmitting, 160 bits per second. The power output from the plutonium has dropped to roughly 220 watts, less than half the original 470. Instruments have been turned off to conserve energy. The cameras went dark in 1990. The ultraviolet spectrometer, the infrared spectrometer, various heaters. The spacecraft are operating at temperatures well below their design specifications, and yet they function, still measuring magnetic fields, cosmic ray intensities, plasma waves, still transmitting data every single day. The operations team is small now, a handful of engineers and scientists. Most of the original team has retired or passed away. Marcus Aldridge died in 2019, 82 years old, peacefully, in his sleep. His obituary mentioned his work on Voyager, but it could not capture what it meant. The 12 years of calculation. The dream that tato and was resurrected. The machines that outlasted their creator. Daniel Brennan is 75, still consulting, still tracking the frequency drift. Though younger engineers have taken over the day-to-day operations, Eleanor Whitmore is 86, living in a care facility near Pasadena. Her mind is still sharp, still asking questions, still wanting to know what Voyager sees. Evelyn Katz is 73, retired, but she still answers emails from the current Voyager team, explaining code she wrote 40 years ago, answering questions about systems only she fully understands. Every Friday, engineers at JPL have a ritual. They listen to the telemetry. As long as they hear the signal, the Voyagers are alive, and the signal keeps coming, faint, steady, reliable. A 23-watt whisper from the edge of everything. Sometime in the early 2030s, the power will drop below the threshold needed to run even a single science instrument. The last data will be transmitted, the last bits will be received, and the deep space network will listen for a while, hoping for a stray signal. Then it will point its antennas elsewhere. Voyager will still be out there, still moving, still carrying its golden record, but it will be deaf and mute. A message in a bottle, with no one left to read the waves. After that, the spacecraft will drift for tens of thousands of years. Voyager 1 will pass within roughly 1.6 light-years of the red dwarf star Gliese 445 in about 40,000 years. It will not stop. It cannot stop. It has no fuel for braking, no engine capable of decelerating. It will drift past, briefly close, then gone. Voyager 2 will pass within 1.7 light-years of Ross 248 in approximately 40,000 years. In about 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius, the brightest star in Earth's night sky. By that time, human civilization will either have expanded across the galaxy or vanished entirely, or evolved into something unrecognizable. The Voyagers will not know, will not care. They will still be drifting, still carrying their records, still intact in the vacuum that preserves all things equally. The golden records are designed to last at least 1 billion years, protected from erosion and oxidation by the hard vacuum of space. 1 billion years from now, the sun will be about 10% more luminous than today. Earth's oceans may be beginning to evaporate. Complex life on the planet's surface may be struggling or gone. The Voyager records will still be intact, carrying Chuck Berry and Beethoven and the sound of a human kiss through a galaxy that has rearranged itself around them. But here is the thing that matters. Right now, while you sit here reading these words, the Voyagers are still working. The plutonium is decaying, predictable, unstoppable. The interstellar hum is vibrating the plasma around the spacecraft, 3,000 cycles per second. The signal is traveling, 17 hours from Voyager 1, 14 hours from Voyager 2, and somewhere on a pale blue dot 11 to 14 billion miles behind them, engineers are still listening. Every day, waiting for 160 bits per second from machines older than their children. You cannot feel it. The plutonium does not hiss when it decays. The interstellar hum cannot be heard by human ears. The signal passes through you with zero awareness, but you know it is there. You know that two machines built by imperfect humans with limited budgets are surviving in the harshest environment the universe has. You know that the signal is still arriving. Every day, every hour, never quitting. And in the contest between cosmic indifference and human will, between entropy and intention, between the darkness and a 23-watt light that has been traveling for decades, will won, intention won, we won. The signal is still arriving, right now.